Hello friends, so in this lecture we will learn about regression and some of their regularized versions. So first let me start with the definition of regression or what we mean by the regression. So regression refers to the problem of learning the relationship between some qualitative or quantitative input variables. Let us say it may be a set of vector, like here you are having x1, x2, xn, means your input variables you can have 1, 2 or any number of input variables, and a quantitative. So, please the output variable will be quantitative, whereas input variables will be either qualitative or quantitative. Mathematically we can say if x is the input variables called independent variables, we have to find out a relationship between output variable y, which is your dependent variable. So, we have to learn this functional relationship with some error, means there might be some error also. So, basically given a set of x values corresponding y values, we need to learn this function f. If this relationship is linear, we will say linear regression, else we will say non-linear regression. So, this is a visual representation of linear regression, and here my input variable is from R, means having only one dimension. So, you consider like this, you are having x and let me x is age in years, and then you are having y, let us say that is your salary, and here I am having data of some employee of a particular firm. So, let us say employee 1, age is 25, and let us say salary, let me mention in thousand. So, salary is 90,000. Employee 2, age is let us say 28 and salary is 95,000. Employee 3, let us say age is 30 and salary is 105,000. Employee 4, let us say age is 31, salary is 102,000. Employee 5, let us say age is 35 and salary is 107, and let us say I am having data of these 5 employees. So, what I will be having, I will take on the horizontal axis age, on the vertical axis salary, and I will plot these 5 set of points. So, let us say these points are like this. Now, if I am having a problem of linear regression, what I will do? I will look for the best fitted line using these data points. Let us say this line I am getting. So, it means I am getting a line y equals to a0 plus a1 x, where a1 is the slope of this line and a0 is y intercept. Okay. Now, suppose I am having another employee who is having age 29, but I do not know the salary of that employee. So, let us say this is 28 and this one 30. So, 29 will be somewhere here. So, once I am having this line, I will see, I will put a perpendicular line in vertical direction from 29, age 29, it will intersect this fitted line, and then what I will do? I will find the corresponding y value of this, that is salary. So, this will be the salary of the person having age 29. Okay. So, in other way, fitting the best line means I need to find out the value of a0 and a1 using this set of data. So, once I will be having A0 and A1, if x is 29, I can easily tell about the y. So, this is a simple linear regression model. Once from the given data, I fit my line. Once I am having the line equation, I can predict the value of dependent variable for a given independent value, for which I do not know the value of dependent variable. However, you can have more than one independent variables. So, for example, you can have age, you can have the experience, you can have the education, and then you can have salary. So, again what I will say, it is x1, it is x2, it is x3 and it is y, and then I am having data of different employees. So, now my y is a function of not only x, but it is a function of more than one variable x1, x2, x3, means salary will depend on age, experience and education. So, now using this data I have to find out this f. When I will go for linear regression, like in case of one variable I was having y equals to alpha 0 plus alpha 1 x. In this case I will be having alpha 0 plus alpha 1 x 1 plus alpha 2 x 2 plus alpha 3 x 3, and this equals to y. Now, when let us say for employee 1, it is, let me write x 1 1, x 1 2 or x 2 1, x 3 1 and y 1. So, I will be having an equation y 1 equals to alpha 0 plus alpha 1 x 1 1 plus alpha 2 x 2 1 plus alpha 3 x 3 1. Let us say for next employee it will be x 1 2, x 2 2, x 3 2 and y 2. So, I will be having another linear equation y 2 equals to alpha 0 plus alpha 1, and then I will be having x 1 2 alpha 2 x 2 2 alpha 3 x 3 2. In that way, suppose I am having the data of n employees. Finally, I am having the nth equation, which is alpha 0 plus alpha 1 x 1 n plus alpha 2 x 2 n plus alpha 3 x 3 n. So, I will be having this linear system of equations where I am having n number of equations in 4 unknown variables. Okay. So, let me write this in matrix form. So, I can write like this x 1 1, x 2 1, x 3 1 and then I will be having 1 here 1 x 1 2, x 2 2, x 3 2, 1 x 1 3, x 2 3, x 3 3 and so on, and I will be having 1 x 1 n, x 2 n, x 3 n. So, this data is given to me because this is from the given table of the data. Now, I will write my alpha 0 alpha 1 alpha alpha 0 alpha 1. Now, I will write my column of unknown variable alpha 0 alpha 1 alpha 2 alpha 3, and this equals to the dependent variable column y to y up to yn. So, certainly because here I am having 4 unknowns and n number of patterns, n number of employee data, n number of rows, and usually in this case we used to have n a large value. So, n is greater than 4. Let us say this n is greater than equals to 4. We are having data of employees 4 or more than 4 employees. So, I will take this as A, this is alpha and this is y. So, I can have a linear system where A is n by 4. So, it is an overdetermined matrix, or I can say it is an overdetermined system 4 cross 1 and n cross 1. So, I will be having A alpha, this is my column vector alpha equals to y. So, from the previous lecture you know how to solve this overdetermined system. We will use the method of least square. I will pre-multiply by A transpose in both side. So, what will happen now, this A transpose A will become a 4 by 4 symmetric matrix, and this will again because A become 4 by 1. So, alpha will become A transpose A inverse into A transpose y, where this is called pseudo inverse of A. And by solving this, because A is given to you, y is given to you, you can easily find out this value. This will be your alpha. Once you are having alpha, you are having your line alpha 0 plus alpha 1 x 1 plus alpha 2 x 2 plus alpha 3 x 3. Means you are having this linear relationship between x 1, x 2, x 3 and the dependent variable y. I can have calculus approach also in the same way, which will give you the same result. So, I will define an error function which is nothing just y minus alpha 0 plus alpha 1 x 1 1 plus alpha 2 x 2 2 plus alpha 3 x 3 2 square. So, this is I am getting from the first equation, from this first equation. Similarly, from second equation I will be having y minus, this is y 1, y 2 minus alpha 0 plus alpha 1 x 1 2 x 2 2 and alpha 3 x 3 2 and whole square, and so on, plus y n minus alpha 0, let me put this here, this here, yeah. So, left hand side minus right hand side, alpha 0 plus alpha 1 x 1 n plus alpha 2 x 2 n plus alpha 3. So, I am using up to 3 independent variable, it can go up to k. So, you can use k also up to k, okay. But I am giving just an this understanding by taking a 3 dimensional regression problem, and then n and then square of this. So, this is the error function and it is nothing just sum of the square of the residuals. These are the residuals, difference between left and right hand side of a given equation. So, I have to minimize this E and means I have to find out such alpha 0, alpha 1, alpha 2 and alpha 3 which minimize this error function E, and you can see it is a sum of squares. So, E will tend to 0, it cannot be negative. Okay, so, for that we will use simple calculus, del E over del alpha 0 equals to 0, del E over del alpha 1 equals to 0, del E over del alpha 2 equals to 0, and del E over del alpha 3 equals to 0. So, from here what you will get? You will get 4 linear equations, and that is equivalent to this system only, and then you can solve this 4 by 4 4 equations in 4 unknown using the simple linear simple method, means inverse approach, and you can get the value of alpha 0, alpha 1, alpha 2 and alpha 3. So, this is basic calculus approach for linear or multiple regression. So, I hope now the idea of linear or multiple linear regression is clear to you. Now, how to evaluate the fitting, means what kind of fitting we are getting. So, what you are having? You are having x 1, again I will use only 3 independent variable x 2, x 3 and then y. So, this is given to you. Now, you got the value of alpha 0, alpha 1, alpha 2 and alpha 3 using either matrix approach or calculus approach. So, let us say now what I will do? I will so, y are y 1, y 2, y 3 and up to y n, and similarly all these value. So, now whatever value of alpha 0, alpha 1, alpha 2 and alpha 3 you have found, I will check this data again, and let us say I am getting value y 1 star, y 2 star, y 3 star and so on. So, if the fitted model is passing through any of the sample point, means any of the pattern, this there will be white star value will be same as the actual value, or predicted value will be the same as the actual value, otherwise there will be some error, and that error is called residual. Okay. Now, what is mean square error? So, mean square error is nothing, you sum the difference between the actual value and the computed or predicted value and take the mean of this. So, this is mean square error. So, take the average of square error, square of the residual error. More formally we use root mean square error, which is again 1 upon n, I equals to 1 to n, and you are having actual value minus predicted value square, and you take the square root of this. So, this is root mean square error. So, we can use any of this measure to find out the error in the fitting. Another way of measuring the goodness of fitting is using the R square score. So, as I told you, the residual is nothing, just difference between the actual truth value and the predicted value, which you have obtained using the parameters founded by the regression. Okay. So, now you consider the linear regression model only, means where I am having only one variable x as independent and y as dependent. So, obviously, I will be having only two unknown variables here, slope and intercept on y axis. So, beta and alpha, and then you also use a horizontal line at y equals to alpha. So, suppose I got this line after the fitting, this is x, this y, you take this line also. Now, R square is nothing, just 1 minus sum of square residuals which you obtain from model with alpha and beta, and sum of square of residuals from model with alpha only. So, if you are having points like this, So, these are the residual. So, sum of square of all these length will be in the let us say in numerator, and then all these length. Okay, the given by the red color, and square of all these will be in denominator. So, this is the formula for calculating r square. Now, it is very much clear that r square will be between 0 to 1, because this value will be always between 0 to 1, this fractional part. If sum of square of residual means numerator and denominator both are equal, then the value of this fraction will be 1. So, 1 minus 1 0, r square will be 0, and then model is not useful. Whatever model you obtained after regression, that is not at all useful. On the other hand, if sum of square of residual equals to 0, it means your line is passing through all the points, those are given for the regression input points. Then r square will be 1 and model fits all the points perfectly. Okay. You are having 0 error in your model. Okay. And same thing happen if you take the multiple regression linear regression model, means you are having more than one independent variable. So, now one can ask, how large does r square need to be considered as good, because 0 is the worst, 1 is the best. So, what value we should consider as a good fitting? So, the answer is we cannot comment on it, it will depend on context, it will depend on the application, on the data. There is no absolute answer. For hard to predict, a low amount of r square is also considered to be good, and this we will see in the implementation lecture, in the next lecture, when we will implement this concept in Python on some benchmark data. Now, after linear regression come to polynomial regression. So, for that you consider this particular data where I am having, let us say, growing time first day, second day, third day up to 15 day, and the dry weight of the onion bulbs. So, it is my y. So, first day, after first day the dry weight is 16.08, after second day it is 13.83, and so on. Now, if I plot this data here, I am having growing time on the x axis and on the y axis dry weight. So, these are these 15 data points. Now, obviously, this data is not in the shape of a line. Okay. So, let us see some other models to fit this data. So, if I use y equals to alpha 0 plus alpha 1 x, it is linear regression on this data, means I will get a line. Let me take a 2 degree polynomial to fit the data. So, I will be having alpha naught plus alpha 1 x plus alpha 2 x square. The process, mathematical process will remain same. Okay. So, I will be having now 1 x square, this kind of coefficient matrix, and here I will be having alpha 0, alpha 1, alpha 2, and then here again y 1, y 2, y n. So, if I use this model, I got this 2 degree curve which fitting this data. If I go for 4 degree model, I will get this one. So, this is more better than the earlier one, 2 degree one. If I go to 5 degree curve, I am getting this data. So, it is considered to be a very good fitting for this data. However, one can go for higher and higher degree and want this kind of fitting. So, this is an overfitting. So, this is when you are using y equals to alpha 0 plus alpha 1 x and go on up to alpha 10 x raised to power 10. So, 10 degree polynomial, even in 11 degree polynomial, up to 11 degree polynomial. So, this is overfitting. Yeah, your residual error is 0, you are having r square equals to 1, but there is an issue. What is the issue? Let me show it here. So, suppose I take a point here and I ask, okay, according to this curve what will be the value of dry weight for this after 1.5 day. So, according to this curve I will get this value, but is it really true value? Because after 1 day I am getting this value. So, weight will increase and after 1.5 day I am getting this one. So, I am getting a good fitting, my training error is 0, but prediction is very poor. Such kind of phenomena is called overfitting. So, you have to make the way that you have to make a model in such a way that it should not overfit. So, in that way I will say that this 5 degree is enough. There might be some residual error, some training error, but it can generalize or it can predict the test data in a good way. So, this is polynomial regression. Now, as I told you, you should avoid the overfitting. Okay. So, how to avoid this overfitting? Because from the data you should not you will not able to see means how to avoid this overfitting. Okay. So, this the concept of regularization is our first weapon to combat overfitting. Okay. So, it constrains the machine learning algorithm to improve out of sample error, especially when noise is present. So, for example, here the same kind of, you can see this red curve is giving you the overfitting. Ideally, it should be the blue one. Okay. So, when you are not using any kind of regularization, you are getting this kind of red curve. But when you are using regularization, you can see you are getting your fitted data, okay, as the actual one, as the target data. So, in that way regularization is quite useful. Now, what is this lambda 0.0? This is the regularization parameter. So, let us learn about this. So, here we will learn two approach. I will go through, one is ridge regression approach, another one is Lasso regression. Okay. So, recall the linear regression process. So, there you have to so I have written beta here instead of alpha or a. So, okay, you treat it as beta. So, the model was like this, residual square error. Okay. So, you have to minimize this model, and that is nothing, just I have defined E earlier. Now, in ridge regression model, what I will do, instead of minimizing this one, I will minimize this particular error function. So, what is extra here? The extra is this one. So, it is your earlier optimal least square plus I am having this extra term. This term is called regularization term. And what this is saying me? Here nothing, just I am also minimizing the sum of squares of my unknown variable multiplied by a regularization parameter lambda. Okay. So, what it will do? So, when you will minimize this sum of squares of each each unknown variable, so you will not give any all these unknown variables will be will not increase too much, means in your model there will be no higher weightage to a particular feature x 1, x 2 or x 3 or a particular independent variable. So, it can be seen in this way. So, lambda is a tuning parameter and you can determine it, you can take lambda different value of lambda, like here lambda 0 means it is usual regression problem, but then you can take lambda this one and you can see the effect, and the value of lambda will depend on the data. Okay. So, what will happen, the effect of this particular term is something like it will add a shrinkage penalty of the form this one, okay, and lambda is positive value. So, this has the effect of shrinking the estimated beta coefficient towards 0. It turns out that such a constraint should improve the fit, because shrinking the coefficient can significantly reduce their variance. Okay. So, you will not be having higher variance in your model, and as I told you, when lambda equals to 0, you will be having usual regression problem without any regularization. Another one is the Lasso regression. Okay. So, if you can see the earlier model where I will be having this something like this. So, this thus one significant problem or one major problem in this ridge regression is that the penalty term will never force any of the coefficient to be exactly 0. It means the final model will include all p predicted, because none of the beta will be 0. So, y equals to beta 0 plus beta 1 p 1 plus beta 2 p beta 1 x 1 plus beta 2 x 2 up to beta p x p, all betas will be non-zero. So, I will be having in final model all p, okay, which creates a challenge in model interpretation, because I am having large dimension, all the variables are there. Okay. So, the one of the modern approach alternative of this is Lasso regression, where what will happen, sum of the beta out of the total p will be 0. So, based on the data which is not useful, that is redundant, for that coefficient will become 0, okay, and that is called Lasso. So, mathematically, instead of minimizing the sum of squares of all beta means unknown variables, here I will minimize the absolute sum, means one norm, absolute norm of this instead of Euclidean or L2 norm. So, this is the difference. In case of ridge, I was having lambda j equals to 1 to p, and this is beta j square, whereas here I am having this sum of the absolute values. So, here I am using L1 penalty instead of L2, which force sum of the coefficient or sum of these beta to be exactly equal to 0 when the tuning parameter lambda is sufficiently large. Okay. So, in that way we can see this Lasso regression as a feature selection or feature extraction kind of process also, because by this I come to know that what are the important features, what are the important xi in my model, because the xi for which beta is becoming 0 are not useful. So, that is the Lasso one. So, it gives me sparse solution of the unknown variable or sparse solution, whereas in case of bridge I will got a non-sparse solution. Sparse means sum of the beta will be 0, and geometrically you can see like this. This is the ridge solution which is not 0, beta 1 and beta 2 both are non-zero, whereas in case of Lasso, where I am having L1 penalty, the optimal solution will come here, and here you can see beta 1 is 0 and beta 2 is having some non-zero value. So, here I am having sparsity. So, with this description, let me summarize this lecture. So, in this lecture we have learned about linear regression, multiple linear regression, polynomial regression, and finally, two regularized versions of regression model. One is ridge regression and another one Lasso regression. In the next lecture, we will implement all these in Python. with this let me close this lecture. Thank you very much.